All right, section 15.4 is called Green's theorem. So we're about to hit into 2 or 3 different theorems in the next few sections that are directly a part of the course description. All right, Green's theorem is one of those descriptions. Before I can get into Green's theorem, we need some terminology that Green's theorem is going to use. So to start with, we're going to talk about a few different physical definitions. So here's our first definition of the day. For a plane curve, C equal to the point x, y, such that x is equal to g of t, y is equal to h of t, and a is less than or equal to t is less than or equal to b. C is closed if its 2 endpoints are the same. I.e., g of a, h of a is equal to g of b, h of b. Okay, this is a 2-part definition. I'm going to give you one more definition inside of this one. The curve is simple if it does not intersect itself except at the endpoints. And what this gives us is it gives us 4 pictures that we can draw. We can draw pictures that have one of these conditions and not the other one, that have both of these conditions true, or have neither of these conditions true. So the first thing I want to do is just give you a second to try and see if you can create an image that satisfies these descriptions. So we're going to do one image that is closed and simple, one image that is closed and not simple, one that's simple and not closed, and one that's neither. So not simple, not closed. So try and see if you can draw pictures, 4 different pictures that would match those descriptions, and then we'll see how close everybody is, and I'll give a couple of examples myself. Okay, draw the first one, the closed and simple, right here. You don't have to put it on a coordinate plane. Flip the pen around.
This is it?
Yeah.
Okay.
Okay, so now you guys can't see what Jordan has drawn so far, so I'm going to just show you from the screen and we'll project in a minute. So do you guys see it? Overall, this is a picture of a circle. I mean, and it wouldn't have to look circular, but this is the idea. So in order for it to be closed, it has to actually start and stop at the same place. So, you know, this is the song that never ends kind of thing, right? There is no start, there is no stop on a closed curve. And then simple means that it doesn't cross over itself. Okay, so there's no crossing point except at the very ends where they meet. Can somebody draw me a picture what you wrote for closed and not simple? James? Oh, fantastic. What's that called? Do you remember?
College?
Is it, do you guys remember what that one's called? I always have a time remembering which one it is. Is this,
Kind of.
do you remember? Is it a cardioid?
Cardioid.
Cardioid's what's coming to my mind,
Yeah.
but I don't hold me to that one.
That kind of makes sense because, like, cardio is hard. I don't know.
Kind of looks like one. My image that I have drawn up there actually looks like a figure 8. Okay, so the whole issue is that it has to cross over itself. But again, it's closed, so there's no beginning, there's no end, but it crosses itself somehow. Okay? All right, somebody else draw me a picture for simple and not closed. Be bold. Volunteer. That's like a slogan. It should go on a t-shirt, shouldn't it? It should be a give blood slogan. Be bold. Volunteer. All right. Tally. Other way. Flip the pen around. All right. So Tally drew a shape that looks like a smile or a parabola. You know, whatever. Okay.
Or that.
So it's simple, right? Does not cross over itself. But the ends definitely do not match up. There is definitely a place you have to start and a place you have to stop to get this picture, right? All right, I need one more volunteer to do a not simple, not closed. Is anybody who hasn't volunteered give an example? You have Taylor.
That's the only one I didn't have.
Only one you didn't have. Nathan?
Does this work?
I don't know how to make it crossover.
No, that one doesn't work. This one's also, the one you've drawn right now is still
What is
simple.
one
Yeah.
that-
All right, so I'll give it to Taylor,
Okay.
even though she looked at Tally's answer because she wasn't sure. All right, so now we have an ichthus. Isn't that how you say that?
Jesus
Ichthus?
fish.
Ichthus.
Jesus fish.
It's a Jesus fish. There you go. All right, so this would work, right? Crosses over itself. That makes it not simple, and it has a beginning and an end, which makes it not closed. All right, so these are the different images that we have in our description. We're going to need these descriptions later. There's one more definition that we're going to need, so I need one more definitional thing to write down for you. There they are. All right. Definition number 3, really, because that was a 2-part one in the last one. We say that a simple closed curve C has positive orientation if the region enclosed by C stays to the left of C as the curve is traversed. The curve has negative, I'll draw pictures in a minute. The curve has negative orientation if the region R stays to the right of C. All right, so we're going to draw a simple closed curve. So something circular would be fine. It wouldn't have to be circular. It could look something like that, some kind of big blob, okay? And you can draw the same or different big blob here because I'm going to need two regions to show you two pictures of these. And the region inside, the curves themselves are called C. The area, if you will, inside is the region, and that's what they're calling R here. Okay, so we've got a region inside of a curve. If we go, in this case, it's counterclockwise. Imagine that you're standing on where the arrow is, and you've got your left hand and your right hand out to your side. The curve's area, the region inside, is to your left as you're moving along that curve, correct? So you're standing right here, and you're walking along the curve, and the region itself is to your left as you're walking along the curve. You with me? That's what this is talking about. That's positive orientation. The region stays to your left the entire way you walk around. Yep. You should be able to say counterclockwise. I never saw them write it that way in your book, which I thought was a little bit awkward, but I'm having a difficult time imagining how that wouldn't be the case. So I think you can, but I'm not gonna say that for sure, Caleb, because I'm not thinking of an example. Just because I'm not thinking of an example where it doesn't work. This is the way that they're presenting it, and I'm feeling like there must be a reason for it. And then, of course, if we're going clockwise on this other one, the opposite happens. The region is to our right. So, but if I come across a reason why that's that case, I'll let you know if there's an exception to the rule or something like that. Yes, as far as I can tell, this is an issue of clockwise versus counterclockwise. So, which would have been a much easier way to say it, which is why I feel like there's a reason they've said it the other way, but I'm not sure.
I mean, it'd be confusing if you had like a kind of a spiral thing going.
But then it wouldn't be closed.
Three-dimensional, keep it enough.
It may have something to do with moving in 3 dimensions. There could be something to do with that. That's a possibility, because we wouldn't have a clockwise versus counterclockwise. So they might be doing that for a 3-dimensional extension. That's a possibility. Okay. I have one more piece of information about notation that we're going to be seeing used, and then we actually have Green's theorem. So we will use the notation where it's got a circle around the middle of it, okay, like this, of our function, our vector function. Have you seen it before?
Physics.
Okay. It will be to denote a line integral along a simple closed curve with positive orientation. So this just gives you more information about the curve than you previously had, really, right? It's not giving you or asking you to do anything you haven't already done. It's just giving you more information about the shape around which you're doing this. The curve itself is simple and it's closed, and it has positive orientation. All right, you ready for Green's theorem? Theorem 4.1, Green's theorem, says the following: let C be a piecewise smooth simple closed curve with positive orientation. And let R be the region enclosed by C. Together with C. So we're getting the region and its boundary, right? The region and the curve combined. That's what R is going to be, the part that's inside and the edge. Suppose that m of xy and n of xy are continuous and have continuous first partial derivatives. In some open region D, where R, our region R, is contained inside of D. So D is encompassing something larger than R itself. It's bigger. Then the integral of mxy dx plus n of xy dy is the double integral over our region R of del n del x minus del m del y dA. And what you should notice here again is that this avoids parameters, right? No parameterization if this rule applies. If we can use Green's theorem, we don't have to parameterize something. Now there's a lot of conditions, right? It has to be simple, it has to be closed, we have to have positive orientation, these derivatives have to, or these functions m and n have to be continuous and have continuous first partials and so forth. And there's a lot of conditions upon which we have to have in order to use this. But when we get to use it, it makes things a lot easier. So we're going to do some examples now. You ready? Yes. Yes. You are ready. I know you're ready. You're ready to see how this works and how beautiful things will be. All right. So example. This is the same directions for all the problems. We're going to use Green's theorem to evaluate the indicated line integral. And they give you this sort of for free. Curves are oriented positively unless otherwise stated. We're actually also told within these directions to use Green's theorem, so we're going to be able to. It's not say use it if it works, right? Notice the way the direction actually said that. That's quite helpful. All right, so let's take a look at the first example. We're going to calculate the line integral around the closed curve, simple closed curve C of y e to the 2x dx plus x squared y squared dy, where C is the rectangle from -2, 0 to 3, 0, 3, 2 to -2, 2, and then back to -2, 0. All right, so there's several things we're going to need to do. We're going to need to figure out what this region actually gives me in terms of limits of integration, because this is supposed to turn into a double integral. I'm also going to have to do some partials, right? The directions over here, as they were worded, said that this first one, well, this is actually true, we've been doing this all the way along. This one is m, and this one is n, and the derivative that I'm supposed to be finding is going to be a double integral over a region R, and I'll just write down what we had over here, of del n del x minus del m del y over dA. So I need to find del n del x and del m del y, right? And we'll do the limits of integration after that. So let's just hold tight on those and let's find those first partials first. So del n del x, what is that? 2xy squared sounds good to me. Is that okay with everybody? All right, and now we need del m del y. Yeah, e to the 2x. All right. Now, let's go ahead and figure out, I mean, we're going to have a dx and a dy here at the end. On this one, it's not going to make any difference. I mean, we could put the limits of integration in either order because it's a rectangular region. That's not going to happen all the time. But let's actually figure out what our region actually looks like. So here's my xy ordered pair, coordinate plane. And I'm going to be using the ordered pairs they gave me. So I have -2, 0. I have 3, 0. I have, so here's this one and this one. And then I have 3, 2. And -2, 2. So my rectangular region is right here. Yeah? So what are my limits of integration? All right, so which one would we like to put on the inside? Any thoughts? The one with the 0 without it. You want it without? Okay, so you want to put -2 to 3 on this one? And that would be dx, right? Okay. And then you want the dy on the outside, and then the dy went from 0 to 2. Does that look okay to everybody? If you switch it around and put the 0 to 2 on the inside, that's just fine as well. It doesn't hurt anything. So we're going to integrate then now, just like we did way back with double integrals. It seems like forever that we've been doing this now, right? This is easy stuff at this point. You guys know how to do double integrals just forward and backward, or at least forward. So we need to do an antiderivative of 2xy squared minus e to the 2x with respect to x. What's that going to give me? Huh? Derivatives backwards. All right, what do we have? X squared y squared. Right. Very good. And we will evaluate that from 3 down to -2. Right? Yikes. Now we got to put in 3's and -2's, and there's no 0's to put in either. So, all right, so somebody put in this value. So if I put in 3 in for, and I'm putting them in for x, so be careful about that, I'm going to get 9y squared minus 1/2 e to the 6th. All right, minus 4y squared minus 1/2 e to the -4th. Did I do that right? Yeah, I will have a plus 1/2 after I distribute that. You're right. All All right, so I will distribute that and simplify now what we're getting. 0 to 2, so I have 9 minus 4, that would be 5y squared. And then the other pieces don't combine, so I have minus 1/2 e to the 6th, and then plus 1/2 e to the negative 4th. And all of this with a dy on the end. Okay, now I need to integrate with respect to y. So tell me what I'm going to get.
531 cubed minus 1/2 e to the 6th 1 plus 1/2 e to the negative 4th 1.
What was the last part?
Plus 1/2 e to the negative 4th 1.
Okay, I thought I heard a sign wrong, but you're right. Very good. And we're evaluating this from 2 to 0, starting at 2 and down to 0. Okay, well that's good because I don't have to evaluate at 0 then, right? Okay, so we're just going to evaluate at 2. So we've got 5/3 times 8. 40/3 minus, oh look at that, we're going to have a 1/2 e to the 6th times 2. Yeah? E to the 6th, nice. And then the last one's going to be like that too, isn't it? So we're going to get plus, e to the negative 4th. Well, it ended up very nicely at the very end, didn't it? That was pretty clean. Any questions on that one? All right. I have one more example of these. Same directions, the line integral around the curve C of f times dr, or dot dr, where f is e to the x squared minus y, e to the 2x plus y, where C is formed by y equals 1 minus x squared and y equals 0. Okay, so it starts out looking a little bit different, but it really isn't different. It's just a different form of it showing up or starting out for us. So this is going to be equal to the double integral of del n del x minus del m del y dA. So we're going to start out by finding those pieces then. And we'll figure out, this is over r, we'll figure out what r is in a minute. All right, so del n del x, what's that going to be with our function field that we were given up there, our vector field?
2 e to the x.
Close. Hang on, you missed something.
Those are
Oh, I'm sorry, I think I was looking at it wrong. Which one are you doing? N of x, you're doing this one. Tell me again, Taylor, what you had?
Did you say n of x?
Yeah, I did.
Oh.
I was just thinking backwards when I said it, yes. You had 2 e to the x?
So 2 e to the 2x.
Sorry about that. Yeah, you're right. And then minus, and now we need del m del y. That's the one I was thinking of already. Hmm? No, the dx and the dA will come at the end. Yeah, dA is going to be the dx dy that we want at the end. But we do need dm dy next. It is, it's just -1. And then we're going to have to figure out what this region looks like. So this region starts to, this section, finding these limits on x and y starts to feel a lot like in Calc 2. where you're looking at trapped between curves and rotating solids and things like that. You're going to draw a picture, and you're going to figure out based on your picture what's happening. So this right here is a bad representation, but it's basically the idea. We've got this upside down parabola that crosses at 1 and then at -1 and 1 here. Right? And the other curve that we are supposed to have is y equal 0. So this is my image, and I want the region that's trapped between those two. So this is my region in here, right? All right, so we get to pick. We can do dx or we can do dy, but there's probably a natural choice based on the information we're given. In particular, we're given that this equation is y equal 1 minus x squared, and this equation is y equal 0. So what would you like to do on the inside, x's or y's? Y's, because we've got them solved for y already, right? What's our lower limit of integration for y? 0. And our upper limit? 1 minus x squared. What is our lower limit of integration for x? -1. And upper? 1. Good. And then I've got dx on the outside. And of course, this is just plus 1. All right, so we need to do our antiderivative with respect to y first, which will look like what?
Two
2y e to the 2x plus y. And we will evaluate that at 1 minus x squared down to 0. So at least we have the 0. But we do have to put in the 1 minus x squared, which makes it a little bit messy. It's not awful, but it does make it a little bit messy. So I have 2 times 1 minus x squared e to the 2x plus 1 minus x squared. All right, so we need to simplify that down. So what does that become when we simplify? Let me move this to another slide before y'all start walking me through the next things. We could, but I think we would rather distribute it out instead of pulling it out, because we don't want it in factored form if we're going to have to integrate it.
2e to the minus 2x squared e to the plus 1 minus.
And nothing combines. Right? Yeah, all that. Nothing combines. Now, part of what we've got here, though, is very easy to integrate, and part of it is not so easy. Which part is the not so easy part?
2x squared e to 2x.
Do you remember what you're going to have to do for that? I think you said it too. Yeah, integration by parts. Let's pull everything else apart and do it first, and then we'll keep that piece to do it afterwards. So let's do the antiderivative of 2e to the 2x. Let's start there. What's the antiderivative of 2e to the 2x?
E to 2x.
That's just e to the 2x. What's the antiderivative of 1? X. And then the antiderivative of negative x squared? Okay, does that look okay? And then we still need, and we'll evaluate that, the -1 and 1 in a moment, but we still need to do the integral of the 2x squared e to the 2x dx. I pulled the negative out in front. I'm going to leave the 2 where it is, though, because it's going to be helpful in my integration steps. All right, so integration by parts. You guys caught it, which was very good. What are we going to let be u, and what are we going to let be dv?
U is 2x squared.
Can I let it just be x squared? Are you okay with that?
I'll let you do that.
Oh, thank you. And then I'd like to do the 2e to the 2x over here. I know there's a dx there. Let me move this over and give myself a little bit more space. All right, derivative of x squared. Antiderivative of 2e to the 2x. E to the 2x. Now do you see why I wanted to put the 2 there? Just a little cleaner. All right, so there's a negative outside of this, but then I need u times v, that's x squared e to the 2x, minus v du, which is 2x e to the 2x dx. And lo and behold, oops, I'm sorry, I forgot a dx here. Lo and behold, what happens? Another integration by parts. Before we go getting too carried away, let's distribute that negative that's in front. Okay? So I've already got now negative x squared e to the 2x. I am going to go back and put every piece on the left-hand side that I have, not the left-hand side, but the first three pieces. I'm going to write all those down in a minute. And then I've got plus the integral of 2x e to the 2x dx. All right, so let me come back over here and write these pieces in. All right, so far so good. One more integration by parts, but it almost looks exactly like the integration by parts I just did, right? It's really not that different. I've got u equal to what? X. Du would be dx. dv would be 2e to the 2x dx. And v would be e to the 2x. So this piece coming down here then would be x e to the 2x minus the integral of e to the 2x dx.
You lost it.
Okay. Sometimes it doesn't catch everything when I copy paste. Where did I lose it?
Well, I don't think it's in when you're copying, but on your U's and D's, the first one,
Mm-hmm.
you left out the 2, but you didn't put it back in. 2x squared equals 2x.
Right here?
Yeah, you took out
I
that 2,
put it
right?
here.
Oh, you put it there.
Yeah, so
Okay.
that I wouldn't have to do a fraction. We get to pick where we put it,
I
right?
did it a little bit differently, yeah.
You should still get the same answer, though.
So far, I don't think I am, but we'll see what happens.
That's not good. You should still get the same answer if you factored it out in front or if you included the 2 with the x squared, either way. All right, we are going to do one more integration and then evaluate, and then this problem's history. All right, last step. Or last two steps, second to last step, that's what we're on. All right, I need the antiderivative of e to the 2x.
1/2 e to the 2x.
Yes. And then it would be plus c, but of course we have limits of integration, so we don't need that. From 1 down to -1, correct? All right. So we're going to plug 1 in everywhere and then plug -1 in everywhere. So e to the 2 plus 1 minus 1/3 minus e to the 2 plus e to the 2 minus 1/2 e to the 2. I think that's getting my values of plus 1 plugged everywhere in. And then we have minus e to the -2 minus 1 plus 1/3 minus e to the -2 minus e to the -2 minus 1/2 e to the -2. Did I catch them all? Let me see if it looks like what I have on my paper.
Sure you did.
Yeah, it looks like it.
Wow, it matches what's on my paper. That's a good sign. I think we got them all. A lot of these cancel out, right? Like right here in the middle, e to the 2 and e to the negative, or negative e to the 2 and positive e to the 2, those would cancel. Over here, I have one at the beginning and one in the middle that would cancel. some of the other pieces combine, right? I can combine this e to the 2 and this 1/2 minus 1/2 e to the 2. So that's actually where I'll start with my combining. So I have a positive e squared and I have a negative 1/2 e squared, which would give me a positive 1/2 e squared. I have a 1 and a negative 1/3. That would give me positive 2/3. And then that's everything in the first parenthesis. In the second parenthesis, I have this is minus. I'll leave the minus there just for the moment while I clean it up a little. I have minus 1 and I have positive 1/3, so that's negative 2/3. And then at the end, we have negative e to the negative 2 and negative 1/2 e to the negative 2, which would be negative 3/2 e to the negative 2. And then, of course, that sign is going to distribute and make those both positive. So the result that I'm going to end up with is a 1/2 e squared plus 4/3 plus 3/2 e to the negative 2. Did it work out, Caleb?
No, that's okay.
Maybe we can find it.
That's what I got.
That's what you got.
Yeah.
I'm so glad, Nathan. That's wonderful. All right. This section has very few problems for homework.
Is it the end of it?
Yeah, that's the end of it.
So like 2?
5.
Hey.
You know what?
I'll take that.
I thought you would. Yeah. All right. So this is page 1021. We're doing problems number 5, 9, 12, 15, and 18.
How long is